All right, so let's do the last lecture. We finished last time by, I introduced the 3-qubit code, and then I said that I was going to give you some generalization of that, which has a volume's worth of degrees of freedom in the bulk. And the idea was that I was going to do it for you using a tensor network, which I would use to generate the wave function of the code subspace as a tensor. Okay, so this was the holographic encoding map. And then then the claim was I was going to build this tensor using a tensor network. So as we discussed yesterday, a tensor network is just a bunch of small tensors with order 1 number of indices, and then we contract the indices together in some diagrammatic way to generate the big tensor. So to do that, I first have to tell you what the little tensors are that I'm going to use. So let me just briefly discuss that, and then we'll talk about the network. The tensors that I'll use are called perfect tensors. Okay, so a perfect tensor is a tensor with so it has 2n indices, each equal size. So in the example that I'm interested in, each index will be 0 or 1. And then it has the property that any balanced bipartition is unitary. So that's a rather surprising property for a tensor to have. So for example, say here I have a perfect tensor U, and it's a unitary, say, going from these 3 to those 3. Well, because it's a perfect tensor, then it's also unitary if, say, I take this one and I view it as output, and I take this one and I view it as input, and then I view it as a tensor this way. Then this is also a unitary transformation. And similarly, for any other split of the indices into 3 and 3, or more generally n and n. Now, it's not obvious that perfect tensors exist, right? I mean, it might be that this is just too constraining for this condition to have any solutions. But indeed, perfect tensors do exist. And in fact, a simple example of a perfect tensor is one that we already encountered yesterday. It's the encoding map of the 3-qubit code. So I guess it's square root of 3 times I1, I2, I3, J tilde. So you can check from the form of the wave functions I wrote down yesterday that this tensor is in fact a perfect tensor. So here it's a 4-leg perfect tensor, so we view it as a 2-qubit to 2-qubit unitary. And the unitary that it is actually just the U12 that we were talking about yesterday. And you can check that again in your dorm, or right now if you think the lecture is boring. Now, today I'm going to use a slightly different perfect tensor. So you may recall yesterday I mentioned that, so with qubits I could encode 1 qubit into 3 and recover from the erasure of 1 qubit. I also mentioned that with qubits you can encode 1 qubit into 5 qubits and then recover from the erasure of any 2 of the qubits. So that code also defines a perfect tensor. Let's say I1 to I5, J. I think maybe it's a square root of 5 that goes here. And then we take the encoding map, I1 to I5, with J tilde. And so then since we can recover from the erasure of 2 of the qubits, then we expect that there's a unitary acting on the other 3, which we can use to recover. And so that unitary, which sends 3 qubits to 3 qubits, is our perfect tensor, but which now has 3 legs, 3 to 3. So that's like this one here. All right? Yeah.
Maybe this is a dumb question, but these operators look like they take in like 3 states and then output 1. So are you like taking some
yeah, that's right. So in this business, you always have to be a little bit careful about when you're taking the complex conjugate of things. So indeed, when you interpret this as a unitary, there may be some. I think the states I wrote down are all real. So then in that case, I think we don't have to worry about the complex conjugate. But otherwise, you're right that we do. Yeah. Okay. So perfect tensors have a nice property, which is called operator pushing. So the idea is, say that I have some perfect tensor here, U. Well, I'm kind of tempted. Well, okay. I'm going to draw it from left to right. Sorry. So then the input is going in here, and the output is coming out here. Now, say that I have another tensor here. You know, just some other 6-index tensor, or it doesn't have to be 6. Could be fewer going in here. Well, no, actually, no, it better be 6. Let's say it's 6. Then the claim is I can find a tensor T prime such that that is true. And this is really not rocket science. So T prime is just U dagger T U. And you see it has the property that I said. So, but because this U is a perfect tensor, then I can do this whichever 3 legs the T is contracted with. So any 3 legs of the U, you have it contracted with some T. I can always replace it by a T that's contracted with the other 3 legs. And then the whole big tensor is the same with the contraction of the 2. So if you like, I can take this operator and I can push it through the U. So this is operator pushing. So these comments are now enough that I can tell you. Now I want to turn on the projector. I think it should. Well, let's see if it's on. And this is enough to now tell you how to make the holographic code. Oh, come on, Windows 10. All right. Okay. So the idea is, remember, I want to now make a big tensor network out of contracting together a bunch of these 6-index T's. So here's what I'm going to do. So I'm going to take a pentagon tiling of the hyperbolic plane, which you see here. And just because I can't resist playing around with this a little bit. Right. So now, in the center of each one of these pentagons, I'm going to stick one of my 6-index tensors. So let's do that. All right. So for example, this blue guy here in the center is one of my 6-index tensors. Now, you might say, well, it looks a lot like a 5-index tensor. And that's true. So where's the 6th index? So the key is that the 6th index you should think of as sticking out of the board and pointing at you. So then the indices that are coming out of the blue dots are going to be these J indices on the tensor. So those are the indices that describe, if you like, the bulk degrees of freedom. So the bulk Hilbert space is a tensor product over all of the blue dots, and it has a qubit at each blue dot. All right, that's the bulk Hilbert space. So previously we only had one point in the bulk. So the previous code would have been I just stick my 4-index perfect tensor here, and that's it. Okay? But now you see then, okay, so each one of these has those. And then most of the indices are contracted, as shown. But then when we get to the edge, we cut it off at some finite radius, if you like, some finite graph distance from the center. And then we just send all of the legs out, all of the remaining legs out, and those are the i's here. So those are the CFT degrees of freedom. So this picture is telling you how to literally construct this Tij tensor up here. Okay, and just one more time we have to. I mean, we're in Colorado, so we could just do this for the rest of the lecture and bring in some stuff and. Yeah, right. So we can get in the mood. Yeah. All right. So that's what it looks like when I draw it. When my collaborator draws this picture, it looks like this. But this is good too. So the reason why I like this version is because now it makes it a little more clear. So here the red dots now are the j indices, and then now you can see the cutoff. So then the white dots are the I indices. Now something which is not obvious from the picture, but what is in fact true, is that this map defines an isometric embedding of the J Hilbert space into the I Hilbert space. So what that means is that the states, the J tilde states I define this way, are all mutually orthonormal, right? If we just pick some random tensors, well, random is a bad word. We just pick some tensors. Then it won't be. So we can still. I mean, we could do this construction for any choice of the tensors here, but the states we get at the boundary, depending, like if I put a 0 or a 1 here, they might not be orthogonal quantum states. So, but it's this unitarity property of the tensors which ensures that they are in fact orthogonal quantum states. And so you can prove that, roughly speaking, by just going iteratively out from the center and showing that you always get a complete orthonormal basis. Sorry, not a complete. You get an orthonormal basis of the code subspace. Okay, so why do we like that? Well, okay, I guess because it looks cool. That's one reason why we like it. But an additional reason why we like it is because now we can actually use operator pushing to do bulk reconstruction. So say we have a bulk operator which acts here on the dangling leg. So say let's call this J1. This is the first logical qubit. So from the point of view of this network, that's an operator that acts on one of the legs of the tensor. But I can choose to say, well, actually, it's an operator that acts on 3 of the legs of the tensor. It acts also as the identity on these 2 legs here. Okay? But then that means I can replace it by an operator that acts on these 3 legs using this pushing operation. But OK, that was so much fun. Let's do it again. So now up here, the action here, I can again say, OK, well, now this acts as the identity on this leg and also on the dangling leg here. So then I can push it to these 3 legs. And similarly, here I can push to 3, and here I can push to 3. And then by the time I'm done, I've replaced it by an operator that acts just on this subregion of the boundary. Okay? And that looks a lot like the Rindler wedge. And in fact, it's redundant. So, I picked these 3. But for example, I could have this guy instead could have sent it here, and gone out this way. And then I would have gotten a representation, more along, more over here, right? Which is kind of like my different Rindler wedges representing the same operator. Moreover, you see if I take an operator over here, it's closer to the boundary, and you see indeed I can represent it on a smaller region of the boundary. So you see in this way we can reproduce this sort of structure of the AdS Rindler code, right, where stuff near the center is well protected. You need to screw up this whole big region here if you want to screw up the center. But stuff near the edge is badly protected because I just need to screw up something here in order to screw this guy up. Yeah?
Sorry. Aren't you somehow using or assuming that when you push this first operator, it looks like a product of legs?
No, I'm not assuming that. So yeah, the picture may make it look like that, but this is all just linear algebra. So the operator that I get will definitely not be a product operator on all of the boundary at legs at the end. It'll be something, very non-local thing that mixes them all together. Because I'll sort of be recursively building up the non-locality. Yeah, it's fine because it's all linear. So you can just sort of view, you can just sort of chain these maps together. Yeah.
Can you push it to disconnect it?
Yeah, just hold it 1 sec. Yeah, of course, yes. And yeah, that's very important. So yes.
Yeah, I'm worried actually about that because, here it's
5, and you have 3 pushed. So
Yeah.
2 always have to be next to each other.
Good, yes. Okay, you guys are incorrigible. Okay, here's a picture.
But I worked if you had 6 legs and 3 that were being pushed, where none of the 3 were touching each other, because then you would eventually map to almost all points on the boundary, the rational numbers on the line.
Yeah, that's right. So you could choose to just sort of spread things out in a way where you just get some sort of set of subregions. Yeah, it is very weird, and that's what this whole lecture is going to be about. Yeah. So that's a good question. Yeah, so indeed we can do that here. From the point of view of the AdS-Rindler reconstruction, that's a bit surprising, because it suggests that whether the regions are contiguous or not is not so important. Whereas from the point of view of the Rindler wedge, it kind of seemed like, okay, well, if I have a ball here and I have a ball here, then I just get the union of the 2 Rindler wedges. But here you see this guy, right? If I just take the wedge up here and the wedge down here, like separately, right? Like, so this one, it's not going to get to the center. It'll get me somewhere as in here. And this one also certainly won't get me to the center. But somehow their union does. Okay. And so that suggests that there's more going on here than this AdS-Rindler reconstruction, and that's going to be one of the big points of the lecture. Okay, finally, which is good. Finally we want to learn something more than just solving the bulk equations of motion, right? That's kind of boring. Okay. So the nice thing about these pictures also, so the reason why tensor networks were originally popular is because it really gives you a graphical representation of the entanglement structure of the boundary, right? So, for example, say I want to compute the correlation function, between an operator here and an operator here. Well, the correlation is going to come, roughly speaking, by trying to find the shortest path through the graph. That's kind of going to give the sort of the biggest contribution to the entanglement between stuff here and stuff there. So then you see stuff that's close together is more entangled because there's a shorter path through the graph, whereas stuff out here is sort of less entangled. But because the graph goes into the center, it's still sort of reasonably entangled. Whereas Rahul had asked about matrix product states and things, which you have for gap systems. So there, the network just goes into some finite radius, and then the correlation is exponentially suppressed for guys that are more separated than that. So the fact that it goes all the way into the center is kind of one way of understanding the conformal symmetry. And indeed, right, this clearly preserves some subgroup of the of SL2R, the conformal group. It's a discrete subgroup. Yeah.
What is the expansion parameter that suppresses?
Yeah, good. So for that statement to really be true, we have to take the range of the indices to be large. Yeah. Yeah. Otherwise, it's sort of everything is sort of formally order 1. So, yeah. Okay. So that was fun. So let me do one more thing with this, and then we'll go back to the blackboard. So the last thing I want to do is talk about black holes. Okay, so there's a black hole. Looks like a black hole, right? So again, this gets back to this question of, okay, so if I just do that picture, right? It's all nice, but we're only getting this tiny subspace of the Hilbert space, right? So in particular, like in this, well, I might not get it quite right, but I think you can show, roughly speaking, that as you go to the UV, that K is something like n divided by square root of 5. Okay, so the code subspace is still a vanishingly small fraction of the Hilbert space, right? Because this means that 2 to the k compared to 2 to the n is a very small number, even though they're both large. So what about the rest of the Hilbert space, right? So as I said yesterday, the rest of the Hilbert space is black holes. So here's a sense of how to get to the rest of the Hilbert space. So you do it by removing tensors. So previously, before I removed this tensor, there was 1 qubit input here, right? But once I removed the tensor, now there are 5 qubit inputs. So there's 2 to the 5 states now, where before there were 2. So 2 of those states, of course, are the ones you get by just putting the tensor back. And those are the ones where the black hole isn't there. And then the orthogonal complement of those is the microstates of this black hole. Those are described by the other inputs I can feed in here. And now I can make the black hole bigger by removing more of the tensors. And it's fairly clear that the dimensionality of the black hole is going to grow like the area, because that's what controls the number of inputs. And if eventually I remove all the tensors, now we've got the whole Hilbert space back. And indeed, you see that most of the states sort of come from bigger and bigger black holes. Moreover, you see that if we restrict the size of the black holes, say, so this is sort of a black hole of 1 AdS radius, then you see out here all the reconstruction works fine. So I have an operator here. I can maybe push it over here. I can maybe push it over here. So we still do get the bulk outside of the black holes. But then eventually the black holes get bigger and bigger, and they eat everything. All right. So indeed, there is a picture of the entire Hilbert space here. Yes? Can I have a network of black holes? I don't know. Can you? I don't know. I mean, yeah, you could have more than one. I mean, I could like remove a tensor over here and also a tensor over there. Yeah, I guess, I don't know. Yeah, I'm not sure what else to say, though. Yeah. Yeah. Unfortunately, nothing, yeah. Right, so yeah, that's related to the firewall question. So you see, as several people were emphasizing yesterday, this construction really only describes things at the AdS scale. And inside of an AdS black hole, if you can only resolve things at the AdS scale, you can't distinguish the horizon from the singularity. Because that's a funny thing about AdS, that no matter how big the black hole is, if you jump in, you die in an AdS time, even if the Schwarzschild radius is much bigger than the AdS radius. So I don't know what happens in the interior. I guess I'm fairly confident that you at most get something of order the AdS radius before you die, but that's enough to get to the singularity and resolve the firewall paradox. But on the other hand, you might get less. I mean, it might be just right at the horizon. Generically, you die. And without being able to resolve the sub-AdS locality, I can't tell you the difference. Of course, if I could, I would be happy. I'll also be happy if one of you can tell me. All right. Any other questions? Yes. Oh, are you asking, is it consistent with that? Yes, because, good. So to do the thermal field double, then I have two of these networks because we now have two AdS boundaries, and then I just sew together these green legs between the two sides. Yeah. Yeah.
So these green dots, I think about them as the actual microstates of black holes.
That's right. Yeah.
So if I add something on one of them, then you can just construct it for part of the space.
Well. No, so I mean, so the black hole, so the black hole has entropy, right? So say this black hole, its size is the AdS radius, so it has entropy order n squared. Here, n is something like the range of the indices on the links, right? So clearly, right, if these indices carry more degrees of freedom, then the entropy of the black hole gets bigger, and so roughly speaking, that's where the n squared comes from. And then, because of the isometric embedding I said before, so say this is 0, 0, 0, 0, 0. Then this defines a state in the CFT. And then now if I change this to 1, now I get an orthogonal state in the CFT, and those are orthogonal microstates of the black hole.
I was wondering what will happen if you repeat the previous argument about reconstructing some degrees of freedom in the ball from the point of view of CFT.
Yeah. So good. So the stuff here can indeed be pushed to the boundary, and that's good because the CFT should know about the microstates, right?
But it's just part of it.
Well, it's the. Yeah, I know, but that's because here I've fixed the energy of the black hole, right? So that's talking about a subspace of the Hilbert space where I have a black hole of such and such energy. I mean, if you don't fix anything, then generically the black hole just fills everything, and the green dots are just sitting right at the boundary. Yeah. Okay. Yeah. Maybe one more. Yeah, that's right. So remember the whole thing about the code subspace is like, if I tell you that you're within this subspace, then you can talk about the bulk. But if I don't, then just generically you think there's just a huge black hole seed in everything. And I mean, because the spectrum of the CFT goes up to infinite energy, to the extent that it makes sense to talk about a generic state, right? A generic state should have infinite energy, and it should just be some black hole that ate everything. Obviously, we have to make that precise. We have to put in a cutoff, but then with the cutoff, as any lattice person will tell you, most of the states are sitting up there with cutoff energy. And so those are the black holes that are filling the space. Yeah, that's right. So it has an atypical state where you do. Yeah, that's right. But that's sort of the way it goes. So the smaller the code subspace, the easier it is to talk about the bulk. When the code subspace is bigger, of course, there are still states there where it's just the vacuum. But we like to talk about operators that make sense on the whole code subspace. And so the bigger we make the code subspace, the fewer of those we're going to have. Yeah, so usually the way you should think about it is you choose the smallest code subspace that lets you ask the question you want to ask. Yeah.
But about the scrambling around the black hole, like you just add something close to the black hole.
Well, that's a question that would require me to tell you what the Hamiltonian is, no? Did you hear me tell you what the Hamiltonian is? Of course I didn't. That's because I don't know what the Hamiltonian is. You know, I mean, that was not, you know, so I know a little bit about the Hamiltonian because I think that these states are low energy states. And I think that this one is a high energy state. But that's not very much information about the Hamiltonian, right? I mean, it's something, you know. It tells, you know, I mean, you know, it tells you that these states are sort of like low-energy CFT states, or again, more carefully, the conformal image of low-energy CFT states. But to answer a question like, what's the scrambling time? I mean, again, that's a sort of a sub-AdS kind of question, and I'm, you know, it's about currently it's above my pay grade. All right. So I guess that's all I really wanted to say about the model. So now I'll switch to Rutakinagi, which and that'll be what we'll talk about for the rest of the lecture. All right.
I have a stupid question.
Oh yeah.
So it seems that you have a way to compute certain functions of local operators on the boundary, at least on the spatial slice, without talking about.
Yeah, but not quite, because remember, there's an input on each of these red legs, and depending what I put there, that'll change the correlation function. So to really be able to do that, I have to tell you which state in the code subspace is the vacuum. But you didn't hear me say that. I mean, roughly speaking, I think what you should do is you should feed in a short-range entangled state into all of the red dots, right? Because in the bulk, there's a gap. You know, the AdS scale sets the mass gap, and so everything should fall off exponentially. Yeah, but I mean, a priori here, I could feed in a product state to all of the red dots. I mean, it'd be kind of a silly thing to do, but it's a state that's in the code subspace. Okay. And then can we also put up, thanks. I'm supposed to, oh, I have to do something else first, right? Yeah, I did something here, but yeah, I did, and nothing happened.
I think you probably just can't see it.
Oh, I see. Ah, okay. All right, great. All right, well, I'll use this one first. But can we get more lights on the board? Is it always this dark? No, these guys somehow, right? Yeah. Oh, okay, great. All right, great. So now I'm going to move on to a topic that at first seems unrelated, but then hopefully I'll be able to convince you it's related, although we'll see how far we get before lunchtime. You all probably have heard of Rutakinagi formula, and Matt Hedrick is going to give a whole lecture series on it, so I'm not going to say very much about I'll just tell you what the formula is and say a few words, and you know, if it's unfamiliar to you, don't worry, you'll learn more about it later. So the original RT, or well, okay, I'll call it the original RT. There's some slight subtlety with calling it that. Says that if you take a spatial slice of the CFT and you take a subregion A, then there's a CFT formula for computing the von Neumann entropy of a CFT state here. So it says that S of rho A, so rho A is the reduced density matrix of some CFT state. I will discuss a bit more about which states in a minute. It says that what we're supposed to do in that state is find the extremal area surface, gamma A. Well, so let me say up here. So gamma A is a codimension 2 surface in the bulk. It has extremal area. It obeys the property that the boundary of gamma A is equal to the boundary of A in the CFT. So that's sometimes called saying that the surface is anchored on A. So now in AdS 3, this is pretty easy. So codimension 2 is just 1. So it's just a geodesic, right? An extremal area surface of dimension 1 is just a geodesic. And so this is saying that it's a geodesic which sort of goes from the one endpoint of A to the other endpoint of A. Okay? But then there's one more requirement usually used, which is that gamma A is homologous to A, which means that if we draw this from above, here's gamma A, here's A, then it means there's a spatial surface here, which, okay, I like to call this capital C. Sometimes people make fun of me for writing this letter, but I think it's an allowed Greek letter. So capital C, I think it's capital C, is codimension 1, spatial surface. Okay, so gamma A being homologous to A means there exists such a surface, right? And if you like, it says the boundary of capital CA is gamma A union A. All right. Hopefully some algebraic topologists won't claim at me for missing some part of the definition. Okay. So sorry, that's all maybe a bit much to hit you with all at once, but hopefully the picture makes it clear what the statement is. Or what the definition of gamma A is. Now I have to, of course, tell you the right-hand side of this equation. But having done all that work, now it's easy. We just say it's the area of gamma A divided by 4G. I suppose there's one other thing I have to tell you, which is that if there's more than one such surface, then we pick the one of minimal area. All right. So this is the original Ryu-Takayanagi formula. I'm sure Matt will tell you a lot more about it. Now, personally, I'm not satisfied with the original Ryu-Takayanagi formula for many reasons. One of them being that I don't really know which states it's supposed to be true in. It's somehow the right-hand side is classical and the left-hand side is quantum. So what does that mean, right? I mean, if this is a quantum property of the state, the entropy, then what appears here also should be. What I'm going to use in this lecture is the improved version. To be historically correct, so the version I described here is actually called, so that was why the original was a little bit subtle. This is really the HRT proposal. So RT is Ryu and Takayanagi, and so they discussed only the case where the geometry is stationary in the bulk. And so they didn't talk about extremal, they just said minimal area surface. But what I said here is necessary to make it covariant when it's time dependent. So that was done by HRT. And now very confusingly, this is Hubeni, Rangamani, and Takayanagi. This is Ryu and Takayanagi. Okay. This is the Hubeni who you may have heard about on the internet in the last few days. Hopefully you didn't. Now the quantum version of RT, and unfortunately this one has yet another acronym, FLM. So that's Faulkner, Lukowitz, and Maldacena. And so just to say, so from now on, I'm just going to say RT. So that's a disservice to Hubeni, Rangamani, Faulkner, Lukowitz, and Maldacena, but whatever, they're all famous, so they'll be okay. And it's too confusing otherwise. So I'm just going to call, what I write now is the RT formula for the rest of this talk. It says that for good states, rho, we have that S of rho A is equal to the expectation value in the state rho of an operator I'll call L sub A plus the entropy in the bulk of rho on this surface capital C of A, where LA is equal to the area of gamma A over 4G, now viewed as a quantum operator on the Hilbert space, plus higher order corrections in G and maybe in alpha prime, which I won't discuss explicitly, but for example, Xidong is the world expert in computing. at least currently. There's a whole industry of people who like computing these terms. Going back a long time to Wald, Jacobson, Myers, I don't know. There's a long list of people who, Solodukin is another one. I don't know. Okay, so this is for our purposes the Ryu-Takenagi formula. Yes.
I'm a bit confused about the complaint of quantum versus classical. It's always the origin.
No.
Something quantum field theory related.
Yeah, but I want to write an equation. So this equation, if you like, there's a leading order piece that's order n squared, and then there's a part that's order n to the 0. Moreover, even at the order n squared piece, we could have superpositions of different geometries. Well, at least in principle, if we could, it would be nice to have a version of the formula that's true also in those. Yeah. That's right. So if you like, the original version should be understood only in states where, from the bulk point of view, you're in a coherent state of the metric, so that both the metric and the extrinsic curvature have small fluctuations. But that's, to me, that's too boring to be interesting. I don't know. Well, it's interesting for some things, but I'm trying to do quantum gravity, so I want the metric to be quantum. All right. So this is the modern Ryu-Takenagi formula. Even so, there are a few things that are still puzzling about it. One, is this good? Come on, right? we should be able to say a little bit better, what are the states where this should be actually true? By now, it probably shouldn't surprise you that I'm going to want to replace the word good by the word code subspace. But there's also something else which I think is even more puzzling, and it's related to the question that people were asking before. Yeah, sorry. Yeah. Well, good. So like most AdS CFT equations, this side is a CFT thing, and this side is a bulk thing. So in the semi-classical gravity theory in the bulk, this is a linear operator on Hilbert space because it's a functional on phase space. Sometimes people get confused and think it's nonlinear because it's a complicated function on phase space. But complicated functions on phase space are still linear operators. For example, the Hamiltonian of the simple harmonic oscillator is p squared plus x squared, but it's still a linear operator. Okay, and this is the same kind of thing, except of course it's even more complicated than that. Okay, but there's an even more puzzling feature of this. Puzzle, which is that in general, gamma A is not contained in the causal wedge of A that we defined, I guess, the day before yesterday. So remember, before we were saying, we had the subregion duality, and we say if you have the stuff that's in A, you have access to the CFT operators in A, then you can figure out what's going on in this causal wedge. Which in the special case of this ball-shaped regions near the vacuum was just the AdS-Rindler reconstruction. But here, this gamma A, it's very easy to come up with examples where gamma A is not inside of the causal wedge of A. So this seems to suggest that the causal wedge is too small. Maybe there's a larger region in the bulk where if I give you all the operators in the subregion A on the boundary, I can also access, I can reconstruct in that larger region what's going on in the bulk, the operators in the bulk. So there's a helpful definition here. So you could ask, what is the biggest thing that it would be reasonable to ask for? And sorry, to be clear, so apparently the entropy in the region A does know about the area of gamma A, so it knows something about it, right? So that's the puzzle, right? Somehow, this is a thing that just is in region A, but somehow it knows something that's outside of the causal wedge. So that suggests that we were being too conservative before when we conjectured that the causal wedge was the thing that was dual to the region A in the boundary. So now let's be ambitious and guess, what's the largest reasonable region that could be dual to A. And so this is what's called the entanglement wedge. So the entanglement wedge, and so this name is from a paper by Hubani, the same Hubani here, and Rangamani, the same Rangamani here, and then Matt Hedrick, who you'll see in a few weeks, and Albion Lawrence. So okay, I could try to put that algorithm. Oh God, alphabetical order. H, L, R. Okay. So the entanglement wedge of A, which we can call W of A to distinguish from C of A, is defined as, well, it's quite simple actually. It's just the bulk domain of dependence of this capital C of A. Okay? So it says we find this HRT surface, or RT surface. I guess people usually call it HRT surface, but call this RT formula. I don't know. So we find this HRT surface. We find this C of A. And then if you remember, the domain of dependence is just the, it's the set of, well, technically it's the set of all the points where any time-like curve through them has to intersect this thing here. But it's just going to be one of these wedge-shaped kind of regions again, right? It's basically the bulk causal diamond of this capital C of A. So if you draw the picture, it actually doesn't look that different from the picture we drew for the causal wedge. And, well, that's actually not a coincidence. The reason is because in the vacuum, for ball-shaped regions, they're the same. Okay? So the reason it looks the same in the picture is because I happen to draw it. The case where I'm capable of drawing it is the case where they're the same, at least the simplest case where I'm capable of drawing it. But in fact, they're not in general equal, and so there's a theorem which is originally due to Aaron Wall, but then was, I guess, proven again by these people, who are maybe a little more clear. Aaron is a brilliant physicist who is years ahead of his time, but then because he's years ahead of his time, sometimes we don't always understand what he's saying when he says it. So the theorem says that the causal wedge of A is always contained in the entanglement wedge of A. Okay? So that means that if we were to conjecture that the entanglement wedge, everything, well, certainly if we believe the causal wedge reconstruction, then, it's never bigger than the entanglement wedge, right? So then it's sort of a reasonable generalization to guess that everything in the entanglement wedge of A is accessible in the boundary region A. So not just the area of the RT surface, but everything else that's in between that and the boundary. So let me just give one example where we can see the difference between the two. One simple example. So the simplest example. So yeah, let's make this some comments on the entanglement wedge. So the simplest example is we consider again AdS3, but now we consider the boundary to be the region to be the union of two intervals. So if the intervals are small, well, we can draw the geodesics. But then there's also another pair of geodesics we could draw, which are like that. Okay? Those are both geodesics that are homologous to A, but the wedges we define are slightly different. So if the regions are small, if these guys are small, then the white lines are shorter than the blue lines. Right? So then the HRT surface is just the union of the white lines. So then the entanglement wedge is just the union of the two separate entanglement or causal wedges. And remember, here the causal wedge, the entanglement wedge is the same if the region is connected. But then as the regions get bigger, so say it's like this, A and A, then now, well, it's the blue lines, which are the minimal area extremal surfaces. So then the entanglement wedge actually looks like this. But the causal wedge, which just takes the two guys separately and makes the Rindler wedge, would still just be this smaller region. So once the intervals get big enough, then the stuff in the center now becomes accessible. Whereas if you have entanglement wedge reconstruction, whereas if you just have causal wedge reconstruction, then still, even in this regime, you don't have access to the center. Okay. So here they're really quite different. Yeah. Which particular thing? You mean the jump here?
Yeah.
Yeah, in some sense there is. I mean, it makes some. So it means that there are some funny phase transitions in some of the entropic quantities you can compute. For example, I mean, one thing you could study, for example, is you could study the mutual information of these two regions. And so, well, mutual information is defined in general as SAB minus SAB plus SA plus SB. So if the extremal surface for AB, which is here just these two taken together, is just these guys, then it just cancels these two and the mutual information is 0. But then once you cross, then it switches. So now SAB is coming from this, but SA and SB are still coming from that. So then this mutual information jumps discontinuously from being order 1 to being order n squared. And so that's, if you like, a large n phase transition in the CFT. Okay. So that's one fun comment about the entanglement wedge. Another comment, which I think is even more important, is that W of A can see beyond horizons. So let me draw an example of that. So let's consider one of these wormholes where I won't draw the thermal field double. It'll be one of these longer wormholes where there's some matter in the center, which is supporting the geometry. So I guess the most famous construction of these kinds of things is by Schenker and Stanford. So then, well, if we think about what's the causal wedge in the boundary, remember, good. So now we'll just take A to be the entire right boundary. So the whole boundary is a union of two spheres. We just take our region A to be one boundary. So by definition, the causal wedge has to be outside of the horizon, because if you remember, the causal wedge was defined as the set of points in the bulk which can both send and receive signals from the boundary. But anything behind the horizon clearly can't send signals to the boundary, and so it's not in the causal wedge. Okay? So C of A is in here. It's the black hole exterior. But if we ask where is the entanglement wedge, well, okay, so to do that, you have to find this minimal area or extremal area surface homologous to A. It turns out that's just the sphere sitting right here in the center of the diagram. So then our CA can be taken to be something like that. And then the entanglement wedge is actually this larger region here. So for entanglement wedges, horizons are no obstruction. So I think that's really probably the thing that makes this question so interesting, is it says that if it's possible to reconstruct in the entire entanglement wedge, as suggested by the Rutakyanagi formula, then perhaps this is a way of thinking about how to understand the interiors of black holes in AdS CFT. And in particular, somehow, the defining property of the horizon, which is that by solving bulk equations, we can't get out if we're behind it, isn't an issue if our reconstruction method is not solving bulk equations, right? Which is what we were doing in the causal wedge. Okay, so now, so that's the entanglement wedge. So now I'm going to make a claim. And then we're just going to spend the rest of the lecture saying a few things about the claim. So the claim is that the RT formula which by that I mean the quantum RT formula, is actually, not only does it suggest entanglement wedge reconstruction, it's equivalent to it. Reconstruction. And so this is something which I would say was, well, this direction was proved in a paper by Xidong and myself and Aaron Wall, and then the equivalence was proven by me last summer. So we can say this in another way, right? Because this, we spent all yesterday deciding that this is basically the same thing as quantum error correction. So then this is basically saying that whenever you have quantum error correction, you have something like the RT formula and vice versa. So the general proof of this is quite general. It uses von Neumann algebras and is general enough to apply directly in AdS CFT. Which means that since we have an independent proof of the RT formula from Lukowitz and Maldacena, well, Faulkner, Lukowitz, and Maldacena in AdS CFT, we now have a proof that in actual AdS CFT, entanglement wedge reconstruction is correct. Now, to go through that, it would take quite a bit of quantum information machinery, which I'm not going to get to in the last 10 minutes. So I think what I'll do instead is I'll just show you that this is true in the 3Q-trit code. So we'll show you that the 3Q-trit code obeys the RT formula. Yes? So what? Oh yeah, but yeah, we can just put a UV cutoff in the CFT. It's fine. Yeah. Oh, I have 25 minutes, do I? Oh, until noon. Oh, well, that's okay. I think still to explain it in the 3Q-trit code at 25 minutes, I can explain it better in 25 minutes. Yes?
In the quantum corrected case, does it matter like which surface you're using, like which surface do you generally use?
Oh, the XIA? No, because so that's a general property of quantum field theory that that entanglement entropies are really defined in diamonds, not on slices. So I could have a Xi like that, but I could also pick that one, and the entropy is the same because they're just related by unitary evolution.
No, I meant like the external surface in correction.
Well, no, I mean the rule here is we just pick A, right? So we just pick the subregion.
I think you're going to take the classical geometry and take the external surface of that. You're going to do like re-extremize the whole.
Oh, good. Yeah. So right. So technically, the formula that I wrote here, this is true at order g to the 0. But if we try to go to higher orders in g, then this needs to be modified. And there's a so maybe I'll just say so the all orders extension of this formula was conjectured by Netta Engelhardt and Aaron Wall. And then just recently, it was proven, I think, by Xidong and Aitor Lukowitz. Yeah. Okay, but I'm not gonna discuss that. But it definitely adds interesting things to the story, and we don't understand the details of it yet. Yes. Okay. All right. So what I'm going to do now is try to illustrate this connection between Rutakinagi and quantum. Did everyone see this? If you don't have a copy card, please see me, Yen Vo. I have no idea what that means, but okay. Classical cloning, yeah, good. Yeah, it's true. Classical cloning is a very practical thing, It makes the archive much easier. Okay. I think I'll just do this way. Okay. So now let's understand this from the error correction point of view. So let's start with our 3Q-trit code. What I say can be sort of generalized to the tensor networks, with the sort of meaning that it works better if you replace the perfect tensors by random tensors, which is something that the standard people explain. Some of them are here, I think, actually. I'm not totally sure. That paper has many authors, but I think some of them are here. Okay, so we have our Q-trits 1, 2, and 3. Here are our causal wedges, and so since the regions are connected, we don't have to distinguish between causal and entanglement wedges. So remember that we found that in encoded state, in the 3-qubit code was produced by just taking this U12, well, or I guess last time I wrote U12 times the identity operator, but I'll now adopt the standard practice of not writing times the identity operator whenever it should be there. And then we had the unencoded state psi on the first qubit, and then we had this state chi on the second and third qubit, where, as you probably remember, this chi was a maximally entangled state. Hopefully that's not such ancient history. So now what I'm going to observe, though, is that there's also a mixed state version of this formula. It's not too fancy. You just say that a mixed state, rho tilde, so that's a mixed state on the 3-qubit Hilbert space, but which has support only in the code subspace, has the form U12 rho 1 tensor chi chi 2 3 U12 dagger. Okay, I'll put a box around this. Okay, so hopefully it's plausible that if this is true, that's true. If you write it out, make a mixed state, you'll convince yourself that indeed it's true. So what I put here, remember now, is a 3x3 matrix. It's the sort of the logical mixed state that I'm trying to describe in the bulk. So if you like, that's the state of what's going on here in the center. And then I've encoded it into the CFT by taking the tensor product with chi and then sticking in these U12s. All right, so far so good. So now to think about Rutakinagi, what we're supposed to do is we're supposed to take this state and then take the partial trace, and look at the reduced state just on one or two of the boundary regions, and then see what's the von Neumann entropy. Maybe I should comment. So I use the word von Neumann entropy intentionally. There are people who say that the Rutakinagi formula is about entanglement entropy. This is a very misleading way of describing the formula, and you should never call it that. Because entanglement entropy is only a thing if the state is pure. Von Neumann entropy is the thing that always makes sense, and the formula is supposed to be true in mixed states, so it's the von Neumann entropy. Okay. So now when your future lecturers use the term entanglement entropy, you can heckle them. All right. Good. So good. So now let's. So the first thing we can do is we can study rho tilde sub 3. So rho tilde sub 3 is I take rho tilde, I trace out 1 and 2. So I just have the reduced state on the boundary region. Right. So that's like my rho A before, where A is now just the third qubit. Remember, each qubit, if you like, is sort of a boundary region. And then, okay, the thing to do is to compute the von Neumann entropy. So using this formula, it's pretty easy to compute the von Neumann entropy. So the first thing to notice is that the U12s are irrelevant because we traced out 1 and 2. So we can just compute the von Neumann entropy of 3 for this state. But then we also traced out 1, so that's gone. And we traced out 2. So the only thing we have is we have half of this state chi. And chi is a maximally mixed state. So that means that this is just log of 3. And I suppose if you want to take the log in base 3, then it's 1. But I'll be agnostic about the base of the log. OK. Well, that is what it is. Now let's try and do S of rho tilde 1, 2. And then maybe I should comment that by the symmetry of the code, it's clear that this will also tell you the answers for any 1 or any 2 of the boundary qubits. Well, OK. So now we trace out 3. Well, so first of all, we can again acknowledge that we don't need to care about the U12s, because the von Neumann entropy is invariant under unitary conjugation. It's just a function of the eigenvalues of the density matrix. So we can again forget about the U12s. So we just need to compute it for this state. So now the only thing we've done is we've thrown out 3. So we've thrown out half of chi. And then this is a product state, so the entropies are additive. So there's 2 terms. So again, we get a log of 3 from half of chi. But now we also get the entropy of this rho 1. But remember that S a matrix, this row 1, is the same matrix as this row tilde was on the code subspace. That was the definition of this, because this is just the encoding map of some mixed state on that central qubit. So this is really just S of rho tilde. I claim this is the Ryu-Takayanagi formula. See if I can convince you. So the proposal is I define LA, the area operator, to be log of 3 times the identity, acting on the code subspace. So now let's look at the bulk and compare to the formula. So let's first consider this one. So here, what we're instructed to do is we take the expectation value of the area operator, that looks good, and then we take the entropy of the stuff that's in the entanglement wedge. Right? That's basically what this says. So the entanglement wedge is just the causal development of this. So this is just the entropy of the stuff in the entanglement wedge. But here there isn't any stuff in the entanglement wedge, because there was only one point in the bulk, and it's over there. So good. But now if we do 1 and 2, well, similar story. So the RT surface is the same. Its area is the same, so that looks good. But now there is something in the bulk sitting there, and hey, look, there's its entropy. So apparently the 3-qubit code knows about the Ryu-Takayanagi formula. So I want to emphasize, I mean, this 3-qubit code, it's really remarkable, right? I mean, it's a 27-dimensional Hilbert space, but it has radial locality. It has bulk effective field theory, right? It has subregion duality, has black holes, has the Ryu-Takayanagi formula. So it's pretty good for 27-dimensional Hilbert space. Yeah. Yeah. So that I'm not going to try and reproduce that here. Yeah. So this connection that I'm describing here is proven through order G to the 0. The various mathematical statements have to be modified to take into account the higher order corrections. Yeah, it's something that various people are thinking about. I'm not sure what the final story is yet. Okay, so let me just make a few comments about this. First of all, we saw yesterday that the entanglement in chi was very important for subregion duality to work. For example, if chi had been a product state, then it would have been a bad code. Okay? Here we see that the entanglement in chi is responsible for the area operator, and in particular for the area not being 0. So if you want to have an area operator which is large, and remember that in AdS CFT we tend to think that this term is large compared to that term, then you need a lot of entanglement in chi. Or in other words, you need a lot of entanglement in the code subspace. So if you like, this is one way of thinking about how the fact that sort of you need a lot of entanglement if you want to have geometry, meaning non-zero area, coming out in the bulk. Now, another comment is that in this example, well, this example is a little bit degenerate because, well, depending on whether A has 1 qubit or 2 qubits, either everything in the bulk is in A, in its entanglement wedge, or nothing in the bulk is in its entanglement wedge. So that's a little bit bizarre. So I'll just comment that clearly that's something that would be fixed by going to the tensor network story, right? Because now you have different stuff in the bulk, and maybe it goes this way, maybe it goes that way. Okay. So, and indeed that's true. And in the tensor networks, you can show that the RT formula holds. There's some slight subtlety with that in general, but, well, at least it holds certainly up to little discretization effects having to do with the tensor network. And then you can get rid of those by doing this business of making the tensors random and taking the range of the internal indices to be large. So maybe I'll just write a formula. So to give you a sense of what things end up looking like in that case. So here we had a formula where we said that I tilde was U12 acting on I times chi, right? Where this was 1 and this was 2, 3. So the statement that's true more generally is that, well, now in the bulk, if you like, we have an RT surface here, and then there are input legs which are in the entanglement wedge, and there are input legs which are in the complementary entanglement wedge. There are two kinds of input legs. I guess I use J for both, so maybe I can call this J A and this J A bar or something like that. So then a complete basis for the code subspace is labeled by what's going on here and what's going on there. And then the analog of this encoding map becomes, so here, let's call this the complement of A. It becomes UA times UA bar acting on something interesting. So now we have JA sitting inside of something I'll call A1, JA bar sitting inside of something I'll call A1 bar, and then we have a state chi times A2 bar, where here I've just sort of arbitrarily split A into HA1 tensor HA2 and HA bar into A bar 1 tensor HA bar 2. Okay. So the details of this aren't too important. It's just to show that, and so this is the structure of the tensor network code. So roughly speaking, you can think of these, so you can think of this chi as being the links that are cut by the extremal surface. You can think of UA as being the part of the network sitting here. You can think of UA bar as being the part of the network sitting there. And now it's obvious that the RT formula is going to work again, because we can just do the same calculation, right? So these unitaries don't matter. We have a product state between the bulk stuff and this chi that describes the links. And then indeed, the amount of entanglement in chi, as you would expect, is controlled by the area of the surface. The more links there are, the more links are cut. And now, in the tensor network code, so we can indeed see that in fact this thing is an area, right? Whereas from the Qtrit example, that was not so clear, why I called it an area. All right, so we're done at 12, right? Okay. So let me now just briefly say, let me make one other comment. So the other comment is that both here and there's something which is very annoying, which is that the area operator is a C number, proportional to the identity, right? Whereas, the whole point in quantum gravity is that the metric is dynamical. So if you tell me that the area is the same in all of the states, that's really not very satisfying. Okay. So, and that's true here, and it's also true up here in the tensor network. So maybe just for completeness, I'll draw the picture here so that we can see from the network point of view. So chi is kind of split across here, and then this is UA, and this is UA bar. Here's A and A bar. So there's still only one chi here, which means that for every state in the code subspace, when we split chi, we're going to get the same entropy. Okay, so if you like, the geometry is the same for all the states in the code subspace, which was true in the tensor network. So somehow we want to generalize this in some way so that the area operator can be non-trivial. All right. So now I think I will just close. So there's a whole machinery that goes into generalizing what happened here and showing that this general theorem is really true. So I think what I'll do is I'll just state the theorem, and you may not understand all of the terms in the theorem, but they shouldn't be so ununderstandable that you're just completely lost. And then if you want to understand it, well, you can read my paper, or you can come and bother me before I disappear on Sunday. And I think we'll stop there. But this is just to show that there's stuff that happens in this field that's true and is general enough to actually apply to AdS CFT. So this is going to be, if you like, the main theorem. Okay, so let H, a Hilbert space, be a tensor product of A and A bar. Okay, so this you can think of as the CFT Hilbert space. Then we will have a code subspace, H code, which is contained in HA, in H. And then finally, we will choose M to be a von Neumann algebra acting on H code. Okay, so that word may look scary, but it just means that it's a set of operators which are closed under Hermitian conjugation, addition, and multiplication, and they contain all scalar multiples of the identity. All right, that's not too bad. In infinite dimensions, there are various other restrictions, but I'll just prove the theorem in finite dimensions. Infinite dimensions are for mathematical physicists. So this is just the setup. Now, let me just say a little about the interpretation of M. So M you should think of as being, so here's A, and here's A bar. And M you should think of as being the algebra of bulk operators sitting inside the entanglement wedge of A. Okay? It's convenient. So we can also define something which is called the commutant of M. Okay, so let me also define that. This isn't really part of the statement of the theorem. It's just a definition that von Neumann algebra people know. It's the set of operators on H code that commute with M. Okay, so it's the set of all the operators in H code that commute with M. And so from the bulk point of view, you should think of that as being the operators in the entanglement wedge of the complementary region. Okay, and to be clear right now, so we discussed previously about gravitational dressing and so on. So any operators here, I'll also take all the dressing to be on this side. Any operators here, all the dressing goes to that side. And so then we really expect these bulk operators to be commuting with those bulk operators. That's not necessary for the statement of the theorem, but I just want to make sure we keep in mind why we're proving this theorem. Right? So that's how you should think of these symbols. Okay, so then the theorem says that, okay, then the following are equivalent. Okay, and I want to say from the beginning that it's not going to be a theorem until I say two things. So what always happens when I give this talk is I say one thing, and then someone says, how do you know if that's true? Okay, it might not be true. The theorem is that if it's true, then the other thing is true too. Okay? All right. Okay, so here's the first thing that could be true. The first thing is that for all O tilde contained in M, and for all O tilde prime contained in M prime. So that's, if you like, for all operators in the entanglement wedge here and all operators in the entanglement wedge there, there exists an operator OA on HA. There exists OA on HA and OA bar prime on HA bar such that, okay, and then the such that is going to say that the guy on OA is a reconstruction of O tilde, and the guy on OA bar is a reconstruction of O tilde prime. Okay, but let's write that out since we're being all rigorous and stuff. So such that for all psi tilde in H code, we have that if we act with OA on psi tilde, we get the same thing that we would have gotten by acting with O tilde on psi tilde. And similarly, for the Hermitian conjugate, acting on psi tilde is the same as O tilde dagger acting on psi tilde. And then similarly, if we act with OA bar prime on psi tilde, we get O tilde prime acting on psi tilde. And then, okay, here's where the notation gets really fun. So we have OA bar prime dagger acting on psi tilde is equal to O tilde prime dagger acting on psi tilde. So I'm sorry for the notation. But hopefully it's not too bad. Right. So yeah, indeed, this is just saying that every operator here can be represented here, and every operator here can be represented here. So this is subregion duality, right? This is, if you like, entanglement wedge duality, although it's not yet totally clear that I'm talking about the entanglement wedge. So yeah, in case there are any mathematically minded people here, let me just make a formal comment, which maybe will help some people. So here we have a Hilbert space which we split into a tensor product, and here we have a subspace of the Hilbert space. A priori, there's no relationship between this tensor product structure and this choice of subspace, right? They're just two different things that we define. This is expressing a relationship between this subspace, this factorization, and also this algebra, which also a priori. So this algebra acted here, but a priori had nothing to do with this tensor factorization. Okay, so we're expressing a relationship between them. All right. Okay, so that's the first thing. Okay, the second one is easier to say, so that's good because we're running out of time. So the thing which this is equivalent to says for all rho tilde on H code, there exists an operator L sub A, which is an element of the center of M. So the center of M is the intersection of M and its commutant. So it's the set of everything in M which commutes with everything in M. Such that, oh, actually, no, sorry, it's important, actually, sorry. I have to say these in the other order. There exists LA in M intersect M prime such that for all rho tilde in H code, so it's important that it's the same operator for every rho tilde. That's why I have to say it in this order. What? Sorry, yes, absolutely. There exists such that for every rho tilde in H code, we have that S of rho tilde A is equal to the expectation value of rho tilde L sub A plus something which I'll call S of rho tilde M, and I'll tell you what that is in a minute. And similarly, S of rho tilde on A bar is trace of rho tilde LA plus S of rho tilde on M prime. Okay, and so that looks like a lot like Rutak-Yanagi formula. Let me just say, I'm not going to define these carefully, but this is the entropy of the state rho tilde on the von Neumann algebra M. Okay? This is an algebraic generalization of von Neumann entropy. So von Neumann entropy, as you probably learned about it, has to do with the tensor product Hilbert space, where you say you take a state and then you compute its von Neumann entropy on one factor by doing the partial trace. That is a special case of this, where the algebra in consideration is just all the operators acting on that factor. Okay? But there are more general von Neumann algebras than just the set of all the operators acting on some tensor factor. Those are called factor algebras. The key thing is that this area operator has to be in the center of the algebra, and for a factor algebra, the center is always trivial, which is why we found that the area operator was a C number over there. It's because we took the bulk Hilbert space to factorize into the stuff in one wedge and the stuff in the other wedge. And then this theorem required that this LA was in the center and therefore was a C number. But you see that once we relax that structure in the Hilbert space and we allow it to not be a tensor product, which indeed is what you would expect, because in the bulk there is diffeomorphism invariance and there are constraints. Lattice people may be familiar with that, right? So the Hilbert space of lattice gauge theory does not factorize because when you cut the links, you have to do something that's not gauge invariant. So here it's the same story, but with diffeomorphism invariance. The things that are in the center are indeed things which are associated to what's going on in the place where you cut, for example, the area operator. Okay. But this is an algebraic expression of that. So indeed, this says that you have quantum error correction or subregion duality if and only if you have the Rutak-Yanagi formula. Okay. So the proof of this is fun, but I mean, it would be like another lecture to a lecture and a half to get all the technology working. So I think I'll just declare it. Hopefully it's plausible. We've seen that it's true in these examples. And in fact, this statement now is general enough that it just applies to AdS CFT. We don't have to talk about tensor networks or not having sub-AdS locality or so on. I mean, this applies even there. Okay.
It definitely seems like relativistic better than it has the problem.
No, it doesn't. So yeah. In fact, this is more general than AdS CFT. So AdS CFT is a special case. Yeah. In some sense, it's too general. So you would like to sort of somehow restrict it to put in more properties of AdS CFT. For example, I didn't say anywhere that I got this by extremizing something, right? Whereas in RT, I said that. So somehow that must be some, restriction of what's going on here. Okay, so I think that's basically all I wanted to say. I mean, there are various other things you can enjoy about this formula. You can see how it works in superpositions of geometries, for example. Indeed, it does. You can think about how it works when there are black holes. Probably to me, the most interesting thing about this, indeed, is that this does tell you that the entanglement wedge reconstruction is correct. So there's more to life than solving bulk equations. And so maybe we will eventually be able to learn how to think about the interiors of black holes. So thanks for listening.
Thanks for a great series of lectures. So this theorem, you've proven.
Yeah, this is a true theorem.
Some of what we call theorems.
No, this one is actually, this one is now published in Communications in Mathematical Physics. So it's a theorem. Yeah.
Sounds pretty good to me.
Yeah.
So with this setup, there seems to be some notion of like coarse graining or defining what the effective description is, or it seems like there was two options for that. You could choose H code.
Yeah. Yeah, that's a great question. So actually, that was a. Yeah, that's great. So let me make a comment about that. So yeah, I should have said this and I forgot. So you may remember, if you've thought about these kind of things before, that the split of the entropy into the area term and the bulk entropy term is not actually a thing which is well defined. It depends on your choice of UV regularization. And so, for example, by doing RG flow, you can move entropy from one side to the other. So here we have a nice analog of that, which is that we think about how big we want the code subspace to be. So the thing that's on the left-hand side of this equation doesn't refer to the code subspace at all. It's just the entropy of rho on a subregion. It's just a CFT thing you can compute. But the thing on the right clearly does care about this structure of the subspace and what is the definition of M. So the interpretation of that is by including more UV degrees of freedom, making the code subspace bigger, more stuff gets counted as entropy in the code subspace, and the area term gets smaller. You can roughly speaking see that here, because stuff that you were previously viewing as part of chi is now getting viewed as part of the bulk. And so the area goes down. And so that's the sort of quantum information and interpretation of the RG flow that lets you move stuff back and forth. Yeah. Yeah.
I have a question about this.
Yeah.
So those modes in the bulk describe gravitational modes.
Yes.
So then, once the gravitas gets condensed, the space can be large, so that I have more Hilbert space example for the field theory. But from the other point of view, from the continual fraction, it seems like the tensor nodes are fixed.
Right, that's right. So that would right, and so that's why I wanted to prove the more general theorem. So in the tensor network thing, we saw the geometry was fixed, right, and then we ended up with this C number area operator. But this formalism can apply to a situation where the metric is dynamical, and now the area operator indeed depends. So if you excite the metric and you change the geometry, then the expectation value of this operator can change because it's now a non-trivial operator.
Yeah, I can think about that. I just questioning that why continual fraction is quite gravitational.
Well, so this is still quantum error correcting code, right? So this is what's called operator algebra quantum error correction. So we started with simple examples, but quantum error correction is a very general idea. And it's general enough to allow for dynamical gravity in the code subspace. That's what this says.
One more.
Does it, in de Sitter space? I'm really glad that someone finally asked that question. Right, so you should ask that question every time at the end of a lecture series on AdS CFT. Yes, I don't know how to think about de Sitter space, and it's embarrassing, to some extent. I think that, we still think that holography in some sense is true in de Sitter space, but so something about this machinery should go through. But honestly, I'm not even, my lack of understanding is already at a much more basic level than that, in the sense that although this theorem is general enough to apply to AdS, right, in the explicit examples that I can construct, I can never get this sub-AdS locality, right? And getting that is sort of, well, certainly that, I mean, I think that's almost equivalent as figuring out how to do this in Minkowski space, like say in the BFSS matrix model. And so, yeah, personally, I would first try to understand flat space or a sub-AdS locality in AdS before I would try to understand de Sitter space, just because there's so many confusing things in de Sitter space. You know, I mean, it probably doesn't even exist really. So, yeah. 11-dimensional flat space in large n limit. No, but you can take the limit right where it goes to flat space, can't you? I mean, I agree there's some subtlety there, but I mean, yeah, but I thought in principle, well, maybe you can correct me, so you know much more about BFSS than I do, but I thought that in principle, we think that using BFSS, we can compute the 11-dimensional S matrix. Okay, yeah, I mean, no, okay, that's reasonable, yeah. Yeah, but I mean, somehow, I mean, the nice thing about BFSS, you know, all this stuff about entanglement from geometry, right? We're talking about spatial entanglement in the CFT. And so clearly, what are we going to say if we're talking about something where there isn't any space, right? Like BFSS or SYK or something like that, right? I mean, somehow there's a key thing that we're missing, which we need to understand. Yeah, I mean, we could try to understand it from either starting point. Maybe starting from BFSS is a little easier because we don't have the distraction of spatial entanglement.
We are going to have some discussion in the last time slot in addition to the lecture. So let's thank